This is Jack Jackson. We're going to be looking today at an alternative formula for population variance. So you may remember that this is the basic formula for the population variance. And in some of the previous videos we go over how to visually interpret this and sort of why this is the formula. But if you look, what we have here is we take each data value, we subtract the mean, we square each of those differences, then we add all of those up, and then we divide by how many of them we have. And that's the basic formula for finding the variance of a population. Of course, take the square root of that, and you have what we call the standard deviation. Now what we're going to do here is we're going to do a little algebraic manipulation on this particular formula and come up with an alternative formula. So first thing I'm going to do is I'm going to take this polynomial and just square it out. So if you remember, if you square a binomial like this, you square the first term, you square the last term, you multiply the two things in the middle and double it. Or think of it as x sub k minus mu, times x sub k minus mu, and use the distributive property, also known as FOIL, to work this out. So first times first gives us the x sub k square. Last times last, two negatives make a positive, mu square. And the o and the I are both minus mu times x sub k, and there's two of them, so it adds up to minus 2 mu times x sub k. So this binomial squares out to this trinomial when we square it, but we're still adding all those up. Now if we're adding up a whole bunch of trinomials, we can think of regrouping this where we're only adding the first terms up, only adding the second terms, and only adding the third terms. And they're all over n, so remember if we have three separate fractions over n, that's the same as getting a common denominator and just adding the numerator. So we can split it up and basically use the distributive property to distribute that 1 over n to each of the three fractions. So that's what we've done here. Now let's experiment with this a little bit, manipulate it a little bit I should say. Okay, well this formula doesn't have anything that changes when n is there, so I can just factor out the mu square and I'm just adding up a bunch of 1's. This one, the minus 2 and the mu don't have anything to do with n, so each one of those terms that we're adding up here has a minus 2 mu, like it's a minus 2 mu times x sub 1 plus minus 2 mu times x sub 2 and so forth. Every one of them has a minus 2 mu, so we can use a distributive property to factor that out front. And that's what we basically got right here. So we've used the distributive property to factor here and here. Now what happens if we add up 1 plus 1 plus 1 plus 1 plus 1 n times? Well, that numerator is just n, which is, so we get n over n, that's going to cancel out. Now, what is the sum of the x's divided by how many you have? You should recognize what that is. That's just the mean. So that's another mu right there. Well, mu times mu is mu square, so this is negative 2 mu square. Notice this first term I've just kind of brought it down. But here, n over n is just 1, and 1 times mu square is mu square. So here I can combine like terms, negative 2 mu square plus 1 mu square is negative 1 mu square. Of course, you're just using the distributive property to factor out the mu square and get negative 2 plus 1 is negative 1. And so we get this different formula. Not necessarily better, in fact I'd claim in some ways it's not as good, but a different formula. Okay, so let's see if we can put these, there we go, put them side by side in the box here. So, in both cases, it's the variance, which we represent by this lowercase Greek letter sigma square. By definition, colon equal means defined to be equal. It's defined to be equal to this. Take the x sub k's minus mu, then square them, then add them up, and then divide by n. But we can get the same answer by adding up the x squared, adding up all the x's, taking all the x's and squaring them first, then adding them up, dividing by n, and then subtracting mu squared. I'll tell you what, let's illustrate this real quickly with an example. Okay, so let's suppose we have some x's. Here are x sub k's. Here are our x's, and I'll just make up some numbers here, and I'll have things down here for the sums. Now first we could actually sum these up using Excel. Let's make that a little bit bigger for you to see, and we'll center this up. Okay, so the mean then will be this when we take the 100 equals 100, and we're going to divide by, well, in this case there are 5 data points, so we're just dividing by 5. So that's the mean right there. Okay. Now, if we do the x's, x sub k's minus the mean, here's what we get. So we're saying equal this number, subtract the mean, which is this one. I want absolute reference that, so I want to make sure that doesn't change either row or column for the mean. So when I copy, Control C, and paste, Control V, we get that. Now remember what happens here. When you add those all up, you get 0. Okay. Now what we want to do is take each of those, x sub k's minus the mean, and square them. So it equals the one to the left to the power 2. No, equals the one here to the power 2. There we go. And copy and paste that. And let's just copy this. And we can sum that. Okay, and then we want to divide that by n, which is 5 in this case, and that should be the variance. That's a population. I'm assuming this is a population. So that's the population variance. Okay, now, alternative way of doing this. Okay, so instead of doing it that way, completely different way we could go at this using our alternative formula. So this method that we just used here is using the definition. Now let's look at what the alternative formula has us do. Okay, it has us just square the x's first and sum them, and then divide by n. So let's look at that. So if we go that way, we would do the x sub k and square that. Take each of the x sub k's and square them. So that says this will equal this 12 here squared. And if I copy and paste that, we get that. So this 100 is just the sum of the x's. The 244 is the sum of the x minus the means square. The 2244 is just the sum of the x squares. And I believe our formula says we have to divide that by n. See right there? So we want to divide that by n. Okay. And that's going to be an important number we're going to need to get. But then we can compute the variance also. And the variance this time should be equals this formula. You take the sum of the x squares divided by n, and then we want to subtract the mean squared. And notice that that is also the same thing that we had before here. So that's 48.8 either way. Okay? So it gives you a different way of computing the variance. And of course, if you wanted to do the standard deviation, then either case, once you found the variance, the square root. Now, from a theoretical standpoint, the formula on the left, the actual definition, is a lot more meaningful because, as you remember from our earlier videos, we have explained geometrically what's going on with this formula right here. This one on the right is maybe not quite as intuitive, or it's not as quite as useful from a geometric explanation. From a computational standpoint, either one of them actually works pretty well. And the one on the right particularly was useful back in the days before we had nice, powerful calculators and computers to calculate these things for us. So you'll also still see this sometimes. Now, if I zoom back out a little bit, you can see that I have actually got this set up to where I have given the reasons out to the side here for each step. So here's an exercise. Let's go back and look at that exercise. So the exercise is, if we know the sum of the x squares, the sum of the x's, and n, can we compute the mean, variance, and standard deviation? Well, yeah, it's pretty easy to do. The mean is going to be the sum of the x's divided by n, so it's going to be 12/20ths. That reduces to, what does that reduce to? 3/4, or 75%. Okay, 12/20. And then, well, let's just do that. So you have I mean 60%, 3/5, excuse me. Okay. And then, let's see, what else? What do we need? So 12/20 is the mean, and so that's the mu here. And then the sum of the x squares is 84. So if we want to find the variance, so this one was the mean, what do? We take the sum of the x squares, 84, divided by 20. Okay, minus the mean here squared. And so there's the variance. So you can compute the mean and the variance directly from that, and then the standard deviation is the square root of the variance. There's an approximate value for the standard deviation. Okay, now, well, there it is. I already had it worked out. Okay, now, in a similar manner, basically using the same kind of steps, okay, we can do the same thing for the sample variance. And if you remember, the sample variance had a variation. Instead of n, there was n minus 1 here in the denominator. Of course, it changed to lowercase n because it's from a sample. Capital N, remember, is the size of the population. And x bar is then the replaces mu because x bar is the sample mean, whereas mu is the population mean, and s is the sample standard deviation, whereas sigma is the population standard deviation. So s square is the sample variance, whereas sigma square was the population variance. But it's basically the same steps. We square out the top, expand that out using FOIL, regroup using associative and commutative properties into three sums here, each over the n minus 1. Factor out the stuff that doesn't change as n changes, so the minus 2 x bar here, and the whole x bar square here. When we're summing up 1, we just get n. And here I wanted to multiply by n over n, right here. So then I think of swapping out these n and this n minus 1, which you can do because this is multiplication. Remember, when you multiply, you just multiply the numerators and the denominators. So then I'll get this over n, and this becomes the x bar again. The sum of the 1 from 1 equals 1 to n is just n. And we get this. Notice this is an x bar square. This is an x bar square. Notice they both have the x bar square and the n over n minus 1. You got negative 2 of them here and 1 here, so that makes negative 1 of those. And notice that we have basically the same thing we did before. They have a common denominator of, we can get this common denominator of n minus 1. And so we have x, the sum of the x sub k squares over n minus 1. And then there's minus x bar square, but we also have this factor n over n minus 1. And that's where it's a little different than the other formula, but a very similar kind of setup. So again, we have this alternative formula. Personally, I don't think it's that important because this formula, by the definition, is much more indicative of what's actually going on, and you can see why it is a measure of variability. You should really know this formula here. This is an alternative formula, though, that sometimes can aid in computation, but of course in reality, if we do very many of these computations with very big data sets, we're going to be using some software which will actually just compute s squared directly. But know that you could use this formula or that formula.